So thank you again for having me here. It's a pleasure to be here. I think in all my years of giving talks, I don't think I've ever given a talk in this kind of a grand avenue. This venue is just unbelievable. So thank you again. So what I'll do today is, following up on what Professor Sokadar was talking about, brain-computer interfaces, right? So we'll begin with this picture, right? So essentially, the question we're asking here is, what can you do when you have brains directly interacting with computers, right? And the answer, of course, is this whole area of brain-computer interfacing, and that's a shameless plug there. That's that's actually my textbook that I wrote about 10 years ago, probably already outdated by now, so I need to write the second edition now. But I can give you a couple of examples of where this field has really gone, right? So building on top of the early demonstrations from Dr. Berbaumer and others, like Dr. Fetz. So you can ask the question, like, imagine if you're trying to augment human abilities, and let's say you're trying to build a brain-controlled robot suit, right? So where have you heard that before or seen that before, right? And that's the Hollywood, of course, right? So Hollywood's already done this with Iron Man, right? And even though they don't explicitly say brain-computer interface, but the assumption is, yeah, there is some interaction going on that allows for fluid, seamless interaction with a augmented, bodysuit, right? But what we're interested in is actually trying to see, can some of this kind of technology be made realistic and, of course, help somebody who's paralyzed, for example, right? And that's the genesis for a lot of the research in the field, starting from predominantly from the 1990s is when a lot of this field really took off. And then the second question that second imagination that you could come into is this idea of, what about learning a new skill, right? So imagine learning a new skill, and can you do that by downloading it to our brains, right? So where have you seen this before? And this, of course, is something that is a big deal in the movie The Matrix, right? So the protagonist, Neo, downloads Kung Fu, right? And you can argue, is that realistic or not, and can we really do that or not, and so on. But this actually relates to this idea of neuromodulation or plasticity, as our previous speaker mentioned. So can we actually rewire the brain and have a medical application here, which is for somebody who may have stroke or other kinds of neurological conditions like depression, for example? Can we enhance their quality of life? Can we enhance their mental health, right? And then finally, can we actually convey thoughts directly from one person to another, right? And obviously, Hollywood's again taken the lead on that, right? This is the X-Men with Professor X, right? In fact, if you go back even further, there's Spock and the Vulcan mind meld, right? In Star Trek, if you're a Star Trek aficionado. So the question is, can we actually do this now with the technologies that we have, that we've heard about, right? And that's another thing you might wonder about. And so what we're working on in my lab is this idea of a coprocessor for the brain. So this builds on this general idea. So brain-computer interfaces or neural interfaces are general devices that interact with the nervous system or with the brain. And what we're trying to do is say, okay, can we use the advances in AI right now that we're seeing? Can that be used to enhance these brain-computer interfaces, and essentially, can we leverage the advances going on in that field while at the same time enhancing the quality of life of people that can benefit from brain-computer interfaces? So the idea is to have a general-purpose device. So this is all the components that one might envision. So you may have inputs coming in from the external world. So this could be sensors, this could be the internet, this could be any kinds of information coming in. It could also be information from the brain itself, right? This is the neural recording aspect of it, and that's given by, on this left-hand side, you can see the read aspect, right? So you want to read from the brain. You also want to have information from external sources that are potentially coming in. And what's in this box here, the brain coprocessor box, is the AI, right? So pick your favorite AI. Nowadays, it's neural networks, deep learning, right? And the idea is, can you do pattern recognition? That's what AI is good at, is pattern recognition, right? So can you recognize particular patterns, and can you optimize some loss function or optimization function or reward function, which is what we do in the AI machine learning areas, in the service of whatever the purpose is for that particular brain-computer interaction. And then on the right-hand side, you can see some of the outputs, right, of this. It could be a neural network, or it could be another kind of AI. And we've already seen some examples where the output could be an external actuator, like a robotic arm, for example, would be one example. There could also be an exoskeleton. And then also this idea of feedback, right? So if you have the output of that particular brain coprocessor going back to the brain, then that provides feedback to the brain, right? So that's the bidirectional brain-computer interface idea that we heard about, right? And the whole idea here is, can we use AI as a way to modulate that interaction, right? And how can that happen? How can we facilitate that, right? So we've already seen something like this before, which is, in our lab, we've tried the 3 different ways of interacting with the brain. So the first one is a completely non-invasive one of EEG or electroencephalography. This is a very traditional technology going back to the 1930s, used for sleep analysis and so on. And this was one of the very first technologies in the BCI, brain-machine interface area, to be explored. The other technology, which is some people call that semi-invasive, because you're going under the skull, and this is only done in a hospital, typically done for people being monitored for epilepsy, for seizures. And in this case, the electrodes or the wires are actually on the surface of the brain, and that's called ECOG or electrocorticography. And then finally, of course, microelectrodes are the standard recording technology for the brain going back to the 1960s and so on, where in this case you have an array of these wires, these microwires that are implanted inside the brain, right? So you actually have to go penetrate the brain and go inside the brain. And so here's an example of what you might get if you use a microelectrode array. And so on the y-axis, you can see different neurons, right? Neurons have, in this case, numbers that you're recording from. And on the x-axis, you can see time, right? And this is measured in milliseconds. And each of these dots is one spike, right? Which is an all or none pulse that neurons give out, action potential or spike, right? And you can see that in this case, you're recording from individual neurons. So you do some spike sorting, you figure out, okay, which neurons are you recording from? And so you get the sequence of these spikes, right? And you can compute a firing rate, if you want, by averaging out the number of spikes within some time window, and you get a firing rate, right? So what can you do with this kind of recording, right? And so this was something that was used, about 10 or 15 years ago. People started using these kinds of multi-electrode array recordings and combining it with some kind of AI. So this could be a neural network, or it could also be a classification algorithm, or it could be a regression, even something as simple as linear regression, right? And combine that to control prosthetic devices like a robotic arm, right? And so here's an example from the University of Pittsburgh, where a person who was paralyzed below the neck was able to use their brain signals, in this case the motor cortex, and they had to train to control, in this case, a 7 degree of freedom robotic arm. You can see that up here. And they were able to control these 7 degrees of freedom to, in this case, get up to a 91.6% accuracy for reaching to different 3-dimensional locations. And this particular video, they're actually feeding themselves a piece of chocolate for the very first time. So you can see there's a control of the hand to grab something. There's a maneuvering towards the mouth, and she's able to feed herself for the first time. So that was one of the early, I guess, 2012 demonstrations. And people are working on incorporating feedback, as we heard, so actually feeling what it means to grab something and so on. So this is an ongoing area of research in the field. One other thing you could do with having actual microelectrode recordings, like recording from individual neurons, is to record and stimulate different areas. So if you have stroke, for example, or other kinds of brain injury, then you can see that there may be some connections that are weak or are missing. And what you could do is potentially build an artificial bridge between one brain area and another brain area, or different regions of the same brain area. And by activating, so in this case what they did was for every pulse or every spike you record from, you then send a pulse back to the brain in the different area, right? So you electrically stimulate the other area. And in doing so, there's a phenomenon that is very well known in neuroscience called Hebbian plasticity, so named after Donald Hebb. And so when you co-activate, A and B, and repeatedly co-activate 2 brain areas, it strengthens the connection between the 2 brain areas. And this was an artificial connection that was created by Fetz and others. And they showed that the brain then strengthens those connections between the 2 brain areas, thereby potentially allowing for very targeted neurorehabilitation of the brain directly, right? So it's a pretty promising way to really have targeted rehabilitation if you can do this for particular kinds of neurological conditions. And then what about if you don't want to go for surgery, you actually still want to use a brain-computer interface, and this is where EEG has been quite useful. So in EEG, for example, you get things like this. So you had your coffee, and you're here now, so hopefully you're alert, right? But then, of course, if you are getting a little bored now, you're leaning back in your chair, you may get EEG signals that look like these. These are called alpha waves, right? And I'm really hoping nobody's really in this state, right? This is deep sleep, so I'm just making sure. I think so far, nobody's in this particular state. But this is what EEG gives you are these oscillations or waves, right? And so this needs to be deciphered by the AI if you're really going to use these kinds of signals to control devices. And this is what a lot of people have done in the non-invasive brain-computer interface area. So what we did, this was back in 2008, was we had our own little Iron Man robot. You can see on the left-hand side, this little robot we call Morpheus, right? And this is perhaps an example of the calm technology, in the sense that we were not trying to control the humanoid robot's joints and every little aspect of the human robot. The robot was autonomous to the extent that it could go and grab things and bring it to locations. And all the human was doing was just specify the high-level command, saying, OK, go and get object A or object B, and then bring it back to location A or location B, right? And so the cognitive load was quite reduced in this case because of the AI being used on the robot, in this case, being controlled by its control system. And so you can see here on the right-hand side a person with the EEG cap, and the robot walks around an arena, and then it beams back the images of what it's seeing. In this case, it's just a red and a green block, and the person gets to pick which one they want the robot to pick up. And this was done using a technique called evoked potentials. It's a very standard technique in EEG, where if there's a flash on an object you're paying attention to, then that causes your brain to generate an evoked potential, and the robot is able to figure out, OK, that's the object the person wants. And the same thing again for the location. There's a blue square on the left-hand side there, which was what the person wanted the robot to bring that object to, and so the robot does all the hard work of walking over there and dropping off the object that you wanted. So this was just a proof of concept demonstration that even with something that is as noisy as EEG, you could still start to do some interesting things, right? Obviously, this is not something that you would implement and have at your home, even though I've had several requests for people saying, hey, that's a great way to get beer from the fridge, right, if I just sit on my couch, right? But no, you can't do that yet. And then we also asked this question at around at the same time that, yeah, we have ways of conveying instructions from a person's brain to a robot, but what about sending it directly to another person's brain, right? Because if we could do that, then we have the first proof of concept, of sending information telepathically in some sense, right? Electrically assisted telepathic information. And so in order to do that, we used transcranial magnetic stimulation, TMS, that we've heard about already. And the idea here is quite simple. So if you have this H-shaped coil that you see on this left side, you send electric current through it. It causes a magnetic field, which penetrates the skull, and then that in turn causes an electric current inside your brain. And if you target that to different locations around your head, you can get different kinds of brain responses, right? So for example, if you target that to the back of your head, that's where the visual cortex is, you start to see little spots of light called phosphenes, even though there's nothing in front of you, but your brain creates this activity, so you start to see little bars or little spots of light, right? If you now move that coil to the top of your head where the motor cortex is, and you play around with it, and at some point, you'll start, when you stimulate the brain magnetically, it'll start moving your hand, right? Your hand will start to move. Even though you didn't plan to move your hand, it involuntarily moves, right? And that's because the motor cortex is sending commands to move your hand, right? So this could be potentially a non-invasive way to send information into the brain. And so we actually did this first proof of concept demonstration of a brain-to-brain communication interface, again, back in 2013 or so, where there were two players. There's actually me as a guinea pig on the left, and this is my collaborator, Andrea Stocco, on the right, in two different parts of the University of Washington campus. And the goal here was, I could see what's happening in the game, but I had no control. He could not see what's happening, but he had a keyboard. And so the idea was, can these two brains collaborate to solve a problem? In this case, the problem was there's stuff happening on the screen, there's rockets, and you're trying to destroy them, right, on the right-hand side. And so you can see the coprocessor on the bottom, where one of them is recording and sending information, the other is receiving information and sending information to the brain of the second person called the receiver, right? And this was one of the first demonstrations. On the left-hand side, you can see me imagining moving my right hand, and as that is being decoded, on the left side, you can see Andrea's hand moves, and just ever so slightly, right? Because that's just a stimulation of the motor cortex, but it's sufficient to cause something to happen in the game, which is tapping the keyboard, which causes the desired result in the game, right? So this was just a proof of concept. And then after that, a few years after that, we also did an extension. So why not extend that to multiple people, right? So is that really something you could do? So this was the very first time we had a person, in this case in the center, right, who had both a recording device and a stimulation device, non-invasive in both cases, so EEG and TMS. And then we had two people who were collaborating with that third person, again, to solve a problem that none of them individually could solve. So we're trying to see, can we have collaborative, brain-to-brain interactions where they collaborate to solve a task that none of them can solve. In this case, it was a simple Tetris task, you can see on the right-hand side. And basically, the Tetris task involves rotating, right? So let me go back to that. So basically, you're trying to decide which of these two people can you trust in terms of the information they're sending. And so we deliberately made one of them be more noisy than the other. So the person who was receiving these flashes of light at the back of their head to say, okay, rotate or don't rotate this Tetris block, they had to decipher that information and then decide which of these persons is actually giving the more trustworthy information. So it's almost like a social network of brains, right? So you have some friends who are more trustworthy than others. So this is an example where we were doing that directly with a brain-to-brain interface. So what we're doing is trying to build this very general-purpose coprocessor system, and we're using neural networks as shown at the top. So there's one neural network that is being used to figure out what kind of stimulation pattern to deliver based on what's happening in the brain and other external kinds of information. Another one that you require, it turns out, is, let me go back again. Another one that you use is basically this emulation network, right? So this one actually simulates the effects of what happens when you deliver stimulation to the brain. It turns out this is really important for us to figure out the best stimulation pattern. So you have both a coprocessor network that is the control system that is sending stimulation patterns into the brain, and the right-hand side is like a forward model or like a model of the brain in some sense, right? Of saying, well, here's stimulation, here's what happens as a consequence of the stimulation. And when you couple them together, that's what this neural coprocessor does. It actually is able to solve problems like optimizing the control of a hand, for example, for rehabilitation. So just to quickly go through some applications here. So we already seen examples of restoration of lost function, right? This is the rehabilitation or robotic arm for somebody who's paralyzed. On the right-hand side is the augmentation or amplification aspect of it for somebody who can use these devices. So you could do physical augmentation, maybe have the third thumb being controlled by the brain from the morning, right? Or you could have an additional arm. You could have perhaps, like an octopus have multiple arms and so on. That's physical amplification. You could also do sensory amplification by having sensors like infrared and ultrasound, actually feed directly into parts of your cortex. There could be cognitive enhancements, so memory, for example, or learning. And then speaking of learning, that ties into education and learning, right? So could we actually enhance the speed of learning as people are learning, new concepts like calculus or chemistry and things like that, right? So people are looking at those aspects as well in education. There's the obvious application of VR and gaming. And so that's something that companies are working on, right? Several companies are looking at VR and gaming. And then finally, there's some pretty interesting kind of brain adaptive entertainment. Have you ever thought, okay, I've watched that movie 3-4 times, I'm getting bored. What if that movie changes its story according to your brain signals, right? I mean, could happen. So Netflix, are you listening? Maybe that's what they'll do, right? Or maybe it's Amazon Prime. And then on the right-hand side, there's this whole idea of telepresence, right? So we went through that during the pandemic. We were doing remote work. But just imagine if you could actually have an interface that gives you not just visual information, audio information, but also tactile and smell and things like that, right? So this will completely potentially obliterate the air travel industry, right? So you may not want to go visit Hawaii if you can experience that directly sitting at home, right? So there's those kinds of consequences as well. And then finally, there's some other very interesting applications that require a lot of ethical thought, right? Like lie detection and neuromarketing. And we're going to discuss the ethical and moral issues. I think these are just some of them that I put up here later in the evening event. So these are really important issues having to do with everything from risks and benefits all the way to security, privacy, identity agency, and even social justice issues, right? So if you have these augmentative brain-computer interfaces, these co-processors, who gets them, right? Is it only the people who can afford them, or should governments subsidize, just like you have subsidization of healthcare and education, should augmentation of intellectual capacities be also subsidized? So these are really important issues that the Center for Neurotechnology, which I direct at the University of Washington, we have a neuroethics team of philosophers, clinicians, and medical ethicists looking at some of these issues. So here's the big picture, right? So as humans, we've augmented ourselves, right from the time that we picked up a piece of stone and we started banging it and we started tearing meat apart and so on, right? And this is just to sort of give you a perspective of all the different inventions we've used to augment our physical and mental capacities, memory capacity, and so on. So something like this AI plus brain-computer interface, this idea of a brain coprocessor, is that just an augmentative tool, like it's a natural progression of all the things we've used to augment our capacities, right? Is that one way to look at it? That's something to think about. I think the big question, right, for the century and beyond that is, how will it actually shape humanity, right? If you're really going this route where you have these augmentation of our brain itself, right, not just the physical capacities. And what we really need here are basically a convergence, right, and the theme of this conference. We need a convergence of minds. We need a convergence of disciplines, right? So we need people who are not just engineers and not just neuroscientists, but also people from the humanities, from philosophers to ethicists. And we really need to have that kind of feedback, even art and so on, right? Just really have that feedback to understand, okay, what are the implications of these kinds of technologies, right, that fundamentally alter who we are as humans, right? And so I think I look forward to interacting with all of you. And I thank again the organizers for organizing this great meeting, this convergence of different disciplines and minds, and just thanking my students, collaborators, and funding. And if you're ever in Seattle, please do visit us at the Center for Neurotechnology. Thank you.